Okay, well, as Madeline said, I'm a senior scientist. I work at PathWest, and SpeeDx, Warwick from SpeeDx said, would I be interested in sharing our experience using the SpeeDx Resistance Plus MGen assay here today, and I was happy to do so. As you know, like MicroLab regimes, especially using azithromycin, are widely used as the first-line treatment of MGen infection. However, the emergence of macrolide resistance has complicated MGen treatment. The cure rates for MGen are declining globally, and research has shown macrolide resistance is commonly related to mutations in 23S ribosomal RNA gene. It's identified five common mutations in two positions in the 23S gene. And so we were really interested to have a look at the Resistance Plus MGen test. It's a multiplex real-time PCR that identifies the presence of MGen DNA in your clinical specimen, but also detects those 5 common mutations that have been associated with resistance to macrolide therapy. It's validated for a fairly broad range of specimen types, and it's also TGA registered, which was attractive to us as well. One of the big selling points for us was the fact that it was compatible with all of the instrumentation that we already had in our laboratory, so we didn't need to purchase any additional equipment to have a look at implementing this assay in our laboratory. The way our workflow goes is that we use our Hamiltons to transfer 200 microlitres of specimen into the MagnaPure 96 sample cartridge, and we then do total nucleic acid extraction of those specimens and elute the DNA into a 100 microlitre volume. We include, during that protocol, the internal control that's provided in the SpeeDx kit. So it will control or provide QC for the extraction as well as the PCR that follows subsequently. We then use then it's also fully automated. We inoculate a 96-well plate, 5 microlitres of that eluate. It's inoculated into a 96-well plate that contains 15 microlitres of the MGen Resistance Plus assay. And we can use it on our LC480s or our CFX96s, which is good as well. It provides us with some flexibility there as well. So it's a fully automated workflow for us, which is great, and allows us to provide reasonably good turnaround time. We actually batch our MGen assay into full 96-well plates. It's just a scheme just showing that generally what we'll do is we're able to inoculate 91 specimen eluates into a plate, 81, and we'll dot some negative controls throughout the plate that have also been through the extraction process with those positives. We inoculate 2 wild-type MGens. One is a positive wild-type MGen provided by SpeeDx, and the other is an external QC that we purchase in to monitor quality control, and also 5 mutant. So each of those 5 common mutations, we inoculate those onto every plate as well. And it's cycled on the LC480 or the CFX96. We can look at the raw data off those instruments, but we can also use the FastFinder software package that is provided by SpeeDx as well. It's really easy to use, and we find it really useful. When the results first come off, we can get just an overview of results. I've just popped an example up here. We can see that our assays pass QC. The blue crosses represent the wild-type MGen, so that's our SpeeDx MGen positive and our external QC. Then the 5 mutants signified by the green crosses have been detected. The grey negatives represent valid negative results. I've included up there an invalid result. That's where the internal control has failed, so we know we need to repeat that sample. And on this run, I think we had 4 wild-type MGen positive samples and 1 mutant positive sample. So we can look at the data this way. We also we can look at all the CT values for these as well, and we can look at the curves. So another way we can look at the data, we can drill down into each of these individual results. The data gets represented using the software analysis. We get 3 sort of results. We get our MGen result represented by the orange data. The purple is the detection of the mutations, and the green is the detection of the internal control. This is just an example of a wild type. So we've got a positive signal for the MGen detection and no amplification for the detection of a mutation, and the internal control is amplified, so it's a pass. So a lot of the results we see look like this. This is an example of a mutant detection. So we've got the orange MGen, the purple detection of a mutation, and the internal control. It's another example of a wild type where we've got no amplification of mutation, but we've detected the MGen. This is a negative, so we've just got amplification of our internal control. And this is an example of a failure where something's gone wrong in the extraction or the PCR, so we know we have to go back and repeat this sample. Before we launched, we did a bit of a verification, see how the assay performed in our own hands. We had a look at analytical sensitivity. So we have a commercial whole genome MGen with a known copy number. In our hands, the limit of detection was roughly to 12.5 copies per microliter, or just under 70 copies per reaction. And that compared reasonably well with our in-house assay. So we were pretty happy with the performance there in terms of the analytical sensitivity. So we did some clinical sensitivity, put through a bunch of clinical samples that were positive or negative for MGen, compared it to our in-house, and we got a 93%, keep pressing the wrong one, 93% positive agreement in that clinical sensitivity study, 100% negative agreement, and a kappa value of 0.95. So that was just for the detection of MGen. So we're pretty happy with that. These 5 false negatives compared to our in-house had very late CTs in our in-house. So I think it was probably on the limit of detection of our in-house as well. So there was not a lot of target DNA in the specimen. We had a go at sequencing the 23S for these positives. We got sequence data on 54 of these, and we ended up with 27 that actually had a mutation in the 23S region associated with resistance. And of those 27, the MGen assay resistance detected 23 of those. The 4 that it did not detect were, once again, had CTs in our in-house assay of 37 or later, so there was not a lot of MGen target there. And just for interest of those isolates that we positives that we sequenced, we encountered 4 of those 5 common mutations in that snapshot of the population that we have in our client specimens. So we decided to move ahead and implement this assay in our laboratory. So we launched it in January of 2018. It replaced our previously our in-house real-time for just the detection of MGen DNA, which we'd been running since the mid-2000s. It's just some data showing you MGen PCR cases over the years, including since the launch of the Resistance Plus assay. So since launching the Resistance Plus assay, we've probably done about 20,000 tests, and we've detected MGen in about 3.8% of those, and just over half of those do actually have a macrolide resistance mutation. So it's very prevalent there, which I think is in keeping with other studies in other regions. I should also just say we've seen no significant difference in MGen resistance between female or male patients, and the rates of MGen resistance, macrolide resistance, have been similar in different age groups so far. We get specimens sent from all over the state, although the vast majority of requests for MGen, like over 90%, are from specimens collected in the metro region. But we get specimens from all regions of the state, and we've seen macrolide-resistant MGen in samples from all of the different regions of the state. So I guess I think the assay has performed well in our laboratory. It's fully automated, it's robust, it's allowed us to provide a fairly good turnaround time, even to those remote regions of the state. We're pretty happy with the analytical and clinical sensitivity of it. Continued surveillance to monitor emergence of further resistance is definitely important, and from our clients we have had a lot of interest in whether we can tell them more about fluoroquinolone resistant MGen as well. So at this moment we can do some sequencing, but we're not providing it as a routine service, but there's been a few cases with some of our clients where they've had patients that are really not clearing their infection, not responding to therapy, that we are able to have a look at some of the past C mutations that have been associated with fluoroquinolone resistance, and we have identified those in some of those cases. I was just going to briefly talk about the resistance plus gonorrhea test as well. We're pretty interested in that. So it's a single well test that detects two gonorrhea targets, as well as the GRA sequence that's been associated with ciprofloxacin susceptibility or resistance. The current first-line therapy is ceftriaxone and azithromycin, but the use of ciprofloxacin can become an option if it's known that the infecting gono is susceptible to ciprotherapy. So some of our clinicians have been interested in that information as well. It's attractive to us again because we don't need to buy any new equipment to establish the test in our laboratory. Our current protocol for gono is we screen all of our samples through the Cobas 4800, and anything gono positive we pop through an in-house confirmatory that detects three gono targets. We don't report this, but we do in-house assay to detect PPNG just for surveillance purposes, because in WA, the remote regional areas in the Kimberley, Pilbara and the Goldfields, penicillin resistance is still really very low, so they're able to continue to use ZAP packs for treatment there, but it's important that we continue surveilling that to look for increases in penicillin resistance. So that's sort of what our in-house is at the moment. But we had a look at the resistance plus gono test. We put through 134 samples. We knew we had 93 specimens that were gonopos and 41 neg. We selected these because we had a paired specimen that had gone to Bacdo for MCNS, so we actually had a cipro susceptibility phenotype on gono isolated from those patients. We popped these positives through, we sequenced the GRA region to look at the ciprofloxacin genotype, this S91 mutation, or whether it was there or not. Identified 50 with the wild type or ciprofloxacin susceptible genotype, and 43 with the S91F mutation, or ciprofloxacin resistance, and that was 100% concordant with the phenotype from the gono that had been isolated from those patients. So we popped all those through this assay. We wanted our workflow is off Cobas, but we also have MagnaPure 96s, so we popped them through Cobas and MagnaPure 96 and got 100% positive predictive value and 100% negative predictive value for the detection of gono off those eluates, which was great. And we got really good results for the detection of the GRA genotype or determination of the GRA genotype from those samples, with 99% sensitivity from the Magnapure eluates and 97% from the Cobas eluates. And we ended up with just 3 that had an indeterminate GRA off those 93 gonopositives, and all of those had demonstrated very late CT values in the Cobas and in our in-house assays. So we knew there was not a lot of target there. So I think I better finish up. I just wanted to, in particular, acknowledge Julia Cattell. Julia did a lot of the MGen PCR and sequencing, and Yuki Z did all of the gono PCR and sequencing, and Cara Mini-Smith from the surveillance unit gave me some of that surveillance data. Thank you.